Hey kids, I realized when I was watching back the video that I did not do number 8 well, so I just want to explain it. Low splitting, high splitting. So remember, the greater it is, the more energy. Okay, so remember, when it's absorbed, when light is absorbed, it releases the complementary color. So the higher the energy of the color is added, the lower energy of the light. So I went through and was talking about the things that can affect splitting, and when I did it in the original video, you'll see that I cropped it out because I just kind of ignored this choice here because the three things that can affect splitting are the identity of the metal. More protons in a metal will decrease the amount of splitting. The other is the oxidation state of the metal. The higher the oxidation state, the greater the splitting. And the identity of the ligand. So you see here we have water, 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 and one ammonia. And I was like, well, they didn't give you the spectrochemical series, so we can't really differentiate between the ligands. But to be perfectly honest, we only really need one piece of information to solve that, and that is the color that the complex shows. Because if the complex had great splitting, it means it would be high energy. So let's go ahead and rank these colors of light. Remember that the colors are in order of energy. We say Roy G. Biv, red, orange, yellow, green, blue, violet, with the red being the low energy and the violet being the highest energy of the bunch. So whichever one appears to be the highest energy actually would have the smallest amount of splitting. So I'm going to give these a rank 1 through 4 of the highest to lowest. So violet is the highest, so we'll say it's number 4. Blue comes in next, blue, violet, green. So blue would be number 3, green would be number 2, orange would be the lowest energy. So it wants to know which one has the greatest splitting. Oh, snippety snappity, I guess either way, we come out with the same answer because orange is the lowest energy light, so it would have the greatest splitting. All right, so I thought when I was watching through the video, I was like, oh, maybe I'm wrong because they give you the color of the complex. I didn't even notice that before. But the color of the complex is just confirming what I originally did. So I'm going to talk about that here because why not? Because I deleted that from the video. I guess now I realize I could have kept it in there. So increased protons decreases splitting. Increased charge increases splitting, and a stronger field ligand increases splitting. So we can't use the stronger field ligand, like I said, because we don't have the spectrochemical series, so I don't know which is stronger, water or ammonia. So it's got to just be between the number of protons. So the one with the greatest number of splitting will have the fewest number of protons and the greatest charge. So low protons, high charge. So if you look at iron, it has atomic number 26. Cobalt is atomic number 27. And chromium is atomic number 24. So when I look here, I think what I said was smallest protons, greatest charge, so that could be this one here, but we really don't know. But the only thing we really need to tell us is the color, because if the color produces low energy, then the color absorbed is high, which means you'd have greater splitting. So the answer is indeed B.